Hello everyone, in this video we're going to be learning how to draw Newman projections of butane. It's extremely important to understand how to draw those, how to draw different conformations, and all the terminology that comes along with it. So we're talking about like staggered, torsional strain, the Gauche conformations, and all those things. I have all these things written out here, so we're going to be explaining those one by one, and we're going to be taking an example of butane in this particular case. So Newman projection is actually a way of drawing a different conformational isomers for for alkanes basically, and you can also do it for cycloalkanes, and you would also see for alkenes as well, but mostly it's used for the alkanes. Now, if I take an example of butane, so this is how the butane is going to look like. We got four carbons in the chain. So that's one way for drawing it. Why I cannot draw it like this? So I got this and that, and then it's going up there. So still the same number of carbons, got 1, 2, 3, 4, and we got 1, 2, 3, 4. But obviously, it's more commonly seen drawing it the first way rather than the second way, and that's because some of the conformations are going to be more stable than the other ones, and that's what we're going to be talking about using these Newman projections. So let's try to draw this the Newman projection for the butane, and we're going to be looking through carbon 2 and 3. So you're always going to be told which bond you're going to be looking through. So in this particular case, I'll make like an eye here. So, pretend that this is an eye. Sorry for the bad drawing there. So I'm looking through the bond 2 and 3. So that means your 2 is going to be the front carbon and 3 is going to be the back carbon. And then you got to draw out what's connected to the second carbon, and you can also got to draw out what's connected to the third carbon. So your front carbon is going to be always at the center. So this center right there is going to be your front carbon. And then your circle is going to be the back carbon. So I'll go ahead and draw a circle here. So that's going to be your back carbon in this particular case. And I'll redraw that in a minute, but I just want to show you that you're going to have a front carbon and you're going to have a back carbon. And obviously this front carbon and back carbon, they are connected with one another, as we have shown with the highlights in this structure here. But you don't really see that particular bond when you're drawing the Newman projection. So you just assume that they are connected, but you don't really draw any bond between this front carbon that's shown as in the center and this back carbon that's shown as a circle. Okay, so I'm gonna go ahead and redraw that real quick. So let's say this is gonna be my front carbon. That's gonna be your carbon 2, and I can probably just go and write that down here actually. This is carbon 2, and this other one, the circle, is gonna be your carbon 3. And to make things clear, I'm gonna redraw that so that I can follow that along. So this is gonna be your front carbon. And then this one is going to be your back carbon. Okay, so then when you rotating the bond, so the one way you can get from one conformation to another conformation is by rotating through the single bond, and that's what we're really going to be doing. We have this bond between the second and third carbon, and that's the bond we're going to be rotating by 60 degrees every time, and then we're going to be seeing how many different conformations you can get. And you can either rotate the front carbon or either you can rotate the back carbon. It doesn't really matter, but for the most part I have seen books rotating the front carbon, and that's what I'm going to be doing here. So I'm going to be rotating the front carbon, keeping the back carbon as it is. So let me go ahead and draw out what's on the back carbon, and I'll draw out what's on the front carbon in a little bit. So we have on the back carbon, there is obviously a methyl group. So remember, if I go back, and your back carbon is going to be number 3. So there is a hydrogen there, and there is a hydrogen there, and obviously there is a CH3 there, and that's what we're going to be drawing on those back carbons. So suppose I go ahead and put this biggest group, which is a CH3, that's coming onto the top, and it doesn't really matter where you put that in the beginning. because you will have a different ways of drawing these conformations, but at the end of the day, you will get into all different conformations when you rotate through the bonds. So we got the CH3, and the other two bonds we have on the back carbon, carbon number 3, is going to be the hydrogen, and there's going to be another hydrogen here. So you want to make sure you draw those as far away from one another technically, and that's going to be your initial setup. Now what I'm going to do, I'm going to copy a bunch of these down because I'm not going to be rotating the back carbon. So your back carbon is going to be fixed. So I'm going to draw a bunch of these so that I don't have to draw again and again. So I would probably need 6 actually. So let me just make a space there. I'm going to move this a little bit up there so that I can move this down here, move this down here, and then I'll move that down here. So I have 3 on each line technically. Okay, so I'm gonna call these A, B, C, D, E. So A, B, C, and I'll just call those as we move along. So now what's happening to your front carbon? So in the beginning, I know the front carbon, which is going to be the center here, it's got a methyl group, the CH3 group, and it's got 2 hydrogen, and that's exactly what we really need to draw. So I'm going to go ahead and put randomly, I can put it anywhere, it doesn't really matter. I can go ahead and put in CH3 there. So it's going to be coming off the center, so keep that in mind. So that's your CH3, and then you're going to have a hydrogen coming off here, and then you're going to have another hydrogen coming off here. So that's going to be your one conformation. So now what I'm going to be doing, I'm going to be rotating those by 60 degrees each time. So let's do a 60 degrees rotation here and see what we're going to be getting here now. So let me just move this a little bit to the right side. So when I rotate it to 60 degrees, and keep in mind I'm only rotating the front carbon and keeping the back carbon as where it is. So when I rotate this front carbon by 60 degrees clockwise, your CH3 technically is going to be coming down here. So that's how the motion is going to look like. So when you redraw that, your CH3 is going to be right on this hydrogen, but you don't really draw that right on the top of this hydrogen, but you just draw it right next to it, but it's just still assumed that it's right on the top of that particular hydrogen. And what happens to that hydrogen right there? That goes on right here. So just follow the motion here, and then this goes on right here. So just keep doing it, and after doing that, you want to draw your next conformation by rotating this by another 60 degrees. So keep in mind, we're still rotating the front carbon, and that's always going to be the case. So what happens now? Your CH3 is going to be down here. Okay, and then your hydrogen is going to be down here, and your hydrogen, another hydrogen is going to be down here. So that's going to be your next conformation. So I'm going to do the same thing. I'm going to rotate it again by 60 degrees, and I'll go back to each one of those explaining which ones are Gaussian, which ones are Eclipse, and whatnot. So let's do another 60 degrees rotation. So when you do another 60 degrees rotation, what happens? Your CH3 now comes right here. Your hydrogen goes on the top of that particular CH3 of the back carbon, and then your hydrogen is going to be right here. Okay, so just keep doing it, and it's probably going to be a good idea if you can pause the session and maybe draw the other 2 conformations by rotating by 60 degrees on your own and see how they look like, and then kind of matches with mine. Okay, so I'm going to have the CH3 now right here. CH3 here, hydrogen there, and I'll do one more. So when I do one more, you're gonna get a CH3 right here, a hydrogen right here, and a hydrogen on the top of one another there. So then when you go back again, when you do rotate it again, it's going to go back to your very first structure you have drawn. So what I'm going to do is going to name these guys A, B, C right there. And then we got D, we got E, and we got F. So when I rotate this F again by 60 degrees, what I'm going to get, I'm going to go back to the A. So I'm not really going to draw that. So you typically going to have 6 conformations, and some of those conformations will have the same energy, and we'll talk about those in a minute. Once you have drawn all the different Newman projections, the next job you have to do is to figure out which ones are eclipse confirmations and which ones are going to be your staggered confirmation. And in addition to that, figure out all the terminology we're going to have in terms of antiperiplanar, gauche, degenerate, the dihedral angles and all that. So before we go into anything, I want to talk about dihedral angle. So if I'm focusing on the biggest group I have between the two carbons, the front carbon and the back carbon, so I know there is going to be a CH3 in the back carbon and there is a CH3 in the front carbon. So if I focus on the angle between those two biggest group, it seems to be it's going to be at a 60 degrees angle at this particular time. This particular angle is going to be called a dihedral angle. So I'm just going to go ahead and move this up here. So that's going to be your dihedral angle. And as you rotate it by 60 degrees in conformation B, what was your dihedral angle? So your dihedral angle in conformation B would have been something like this. We have 120 degrees for the dihedral angle in conformation B. So that's one thing you want to make sure you can look into. Whenever you have the two groups kind of close to one another, you will be running into an issues of so-called an torsional strain. If I want to focus on A versus B, in A, the CH3 groups are kind of further away from one another, and also the other groups, for example, I can talk about this hydrogen here and this hydrogen here, they're also separated by 60 degrees. But when I'm looking at B, what's happening? Those two groups right there, those two hydrogens, they have a torsional angle, or you can say with respect to one another, their torsional angle is 0, and as a result, they're going to have a lot of torsional strain. So those particular conformations are going to be your eclipse conformations whenever you have one bond of the front carbon is in parallel to the bond of the back carbon. Focusing on A, what's similar to A in terms of conformation? We have C that have all those groups kind of separated from one another, and we got E that all those groups are separated from one another. So A, C, and E are going to be your staggered confirmation. So I'm just going to go ahead and write that down here. So your A, C, and E would be your staggered confirmations. And what's left behind? Your three other confirmations we have. So we got B, and we have D, and we got F. That's where your torsional strain is going to be maximum, and as a result, they are going to be your eclipse confirmation. So we got B, B, D, and F would be your eclipse confirmation. Now, in addition to that, whenever you have two groups kind of close by in staggered confirmation, so what's going to be the difference between A and E and versus C? I can clearly see here that your um, CH3 groups in case of A and in case of E are in a very similar situation as far as the interactions go, because they have or they are separated by a very similar angle. But when I'm looking at the C conformation, the CH3 groups are actually opposite to one another. So that's when they're going to have almost no interactions, or you can say minimum interactions with one another. But when I'm looking at A and B, A and E rather, you're still gonna have these CH3 groups having some interactions, and those particular interactions are gonna be called Gauche interactions. So let me just draw those out here. So this particular interaction right there and this particular interaction right there, those are gonna be your Gauche interactions. So let me just move that up here. That's going to be your Gaussian interactions. And those particular conformations, the A and E, would be called Gauche conformations. So I'm going to go ahead and write that down here. So your A and E would be the Gauche conformations. And when I'm looking at C, since in case of C, your biggest group, the metal groups on the front carbon and the back carbon, they're opposite to one another, or another way of saying they have a dihedral angle of 180. So if I want to go ahead and draw the dihedral angle between those two particular groups, that's going to be 180 degrees. So that's when they're going to be anti-periplanar. So this particular C is going to be anti-periplanar, and that's going to be typically the most stable conformation in among all the Newman projections. And then when I'm looking at these Gauche conformations, that's A and E. Well, in A and E, you will have very similar type of interactions. These Gauche interactions are kind of the steric interactions you would find in the eclipse conformations. However, when you're comparing the interactions, the steric interactions in eclipse conformation versus the Gauche conformation, the steric interactions in eclipse conformations are stronger than the steric interactions in case of Gauche conformation. So as a result, your Gauche conformations are always going to be more stable than your eclipse conformation. So we'll talk about that in a minute as well. So in case of A and E, since you have a very similar type of interactions, both of these A and E are also going to be the degenerate, which means both A and E are going to have the same energy. So make sure you know what degenerate means. It means it's got same energy, or you can say the same stability among one another. Okay, so we took care of all the staggered confirmation. Now let's focus on our eclipse confirmation. So we got B, we got D, and we got F. Now let's figure out what's going to be the difference between those confirmations. Okay, we have in case of B, we can clearly see we have two interactions where the CH3 group is kind of in parallel with the hydrogen. All right, and then the third interaction is just between the hydrogen and hydrogen. So there is a torsional strain between the methyl group and the hydrogen, and there is an steric interaction between the methyl and the hydrogen. So there's two things going on when you're looking at the eclipse conformations. You're going to have a torsional strain and you're going to have the steric interactions. When you're looking at the Gauche conformations, you're only going to have the Gauche interactions. You're not going to have a torsional strain, or you're going to have a minimum torsional strain in those cases. And when I compare this with the D, what's going to be the difference in the interactions between the B and the D? Well, turns out we have two methyl and hydrogen interactions, and then one hydrogen-hydrogen interactions in case of D as well. So as a result, your B and D dealing with the same type of torsional strain and dealing with the same type of steric interactions, and as a result they will be having the same energy, so they're going to be degenerate among one another. So I'm going to go ahead and write down that B and D are also going to be degenerate. Now remember, degenerate means their energy is going to be the same, but their energy is not going to be the same as that of A and E, and that they're going to have both the torsional strain and they're also going to have the steric hindrance. Okay, let's look at this last one here. When I'm looking at F, what's going on? In case of F, I have two methyl groups interacting with one another. So along with this having the eclipse conformation, which means you already have the torsional strain there because these bonds are parallel to one another, In addition to that, there is going to be a maximum steric interaction because in case of B and D, your steric interactions were between the methyl group and the hydrogen, but now here the steric interaction is going to be between the two methyl groups. So since the steric interaction is between the two methyl groups, that's going to be the biggest interaction in this particular case. So this F is going to be least stable. All right, and keep in mind it's still got the torsional strain and it's still got the steric hindrance. If I want to compare the steric hindrance between, in case of B and D versus F, in both of those cases we have the torsional strain, but if I want to look at the steric hindrance alone, the steric hindrance in case of F is going to be bigger than the steric hindrance in case of B and D, and that's why your F is going to be the least stable out of all the conformations. So when I'm writing out in terms of the stability order, so I know so far what we have said, C being the antiperiplanar is going to be the most stable. So C is going to be the most stable. And then after that, our A and C, A and E rather, they are the Gauche conformation. Remember, your Gauche conformations are always going to be more stable than your Eclipse conformations. But then also keep in mind your A and E were degenerate. So I'm gonna saying C is more stable than E, but then E and A are actually going to be in equal energy in terms of energy. And then these guys are going to be more stable than your eclipse conformations. Now, between the eclipse conformations, we figured out that your B and D is going to be more stable than the F because the steric hindrance in case of F is going to be bigger than in case of B and D. So I'll go ahead and write down it's going to be B, and B is going to be the same as D. And then you're going to have F being the least stable. And you can also say, if I want to write that down in terms of energy order is just going to be opposite. So whoever is the most stable is going to have the lowest energy. So I would say F being the highest in energy, followed by D, and D and B are going to be in the same energy level, and then followed by your E, which is going to be in the same energy level as that of A, and then your C is going to have the lowest energy. And sometimes they would, the question is based on the stability or sometimes based on the energy order. So you want to make sure you know whoever is the most stable is going to be lowest in energy. So if I want to go back to the original question I had posed by drawing those two conformations in the beginning. So remember I have drawn this confirmation right there and that confirmation right there, and then I asked you why would you prefer to draw it the one way than the other. That's because there's two methyl groups that we were looking at. In case of, let me change the color there. In case of first, they are anti to one another. So this particular one is actually resembling to your conformation C. But when I'm looking at the second structure that we have drawn, those two methyl groups are syn to one another, or another way of saying they're eclipsed to one another, and that's going to resemble to your F conformation. So since F conformation is an energy cost conformation, your C is going to be the most stable. Um, Another name for the F conformation, even though it is indeed an eclipse conformation, is going to be the syn conformation where your biggest group are right along the same line in this particular case. Now, if I want to draw these figures that we just got, or these projections that we just got in the form of a diagram, I can have the energy. I can have energy on the y-axis, and then I can have the dihedral angle on the x-axis. So you want to see what happens when you move along the dihedral angle. And in this particular case, the dihedral angle that we're going to be focusing on is going to be between those two methyl groups. Okay, so we know your first one was A, and A was one of the Gauche conformations. So Gauche conformations are going to be more stable than your eclipse confirmation. So I'm going to go ahead and draw this, let's suppose, right here. And then after moving 60 degrees from the Gauche confirmation, we get to this B, which was one of the eclipse confirmation. Now your dihedral angle is at 120 degrees. So I can go ahead and write down 60 here on the bottom. Then I can go ahead and write down 120. I can write down 180, and then I got 240, got 300, and then finally you got 360, which is kind of similar to saying it's a zero, depending on how you measure that particular angle. So A is one of your Gauche confirmations, and then at 120 you get your eclipse confirmation. So let's say I'm going to draw that right here. The eclipse confirmation is going to be less stable or more energetic in case compared to your Gauche confirmation. That's your B. Now, when we're looking at C, what happens? Well, we have determined that C was your antiperiplanar, so it's going to be the most stable. That means it's going to be the least energetic. So I'm going to go ahead and draw that all the way down here. So that's going to be your C. And then moving along, what happens? From C, you go on to D, which D is another eclipse confirmation, but then also keep in mind that D has the same energy as that of B. Or another way of saying they are degenerate. So I'm going to go back up and I'm going to draw the D at the same energy level where your B is. So make sure you pay close attention to that. So that's your dihedral angle of 240. And then moving along, your E is another Gauche confirmation. And what we have said, your E and A have the same type of interactions, and as a result they are going to be degenerate. So I'm going to go ahead and bring this graph down all the way to A, where the position of A is. So this is going to be your E. And then finally, your F is going to be the syn confirmation or syn eclipse confirmation, where the interactions are going to be the greatest, and as a result, it's going to be the least stable. So if something is least stable, that's going to have the most energy. So I'm going to have to go ahead and draw that all the way up right there. So that's going to be your, made it, that should have been E there. I made this as an F, and when you rotate it back, it's going to come back down to A, so you don't have to draw that one. So remember, this eclipse confirmation is going to be the least stable. So even though you have multiple eclipse confirmations, that does not necessarily mean all of them will be at the same energy level. The same can be said to the Gauche confirmations. In this particular case, A and E came out to be at the same level, but if you have different substituents on it, they may not come out to be the same level. And I have another example, and you want to watch that video where we have multiple Gauche confirmations and multiple eclipse confirmations, but none of them were matching with their energies. Okay, so in terms of the energy cost briefly, you don't really have to know the values, and you don't have to really memorize those, but in case you're asked, the hydrogen, when you're bringing the hydrogens together, like in this case, bringing those two hydrogens together, it actually costs, let me change the color here, it actually costs about 4 kilojoules per mole. So what that really means, having these hydrogens further away from one another and bringing them closer, it's going to cost you about 4 kilojoules of energy. Or you can also say when they are separated from one another, that particular conformation is going to be 4 kilojoules more stable. And then keep in mind, you also got to take account of other hydrogen interactions if they are like this particular one is going to be 4 kilojoule per mole as well. When we're looking at your methyl interactions, like in this particular case, their energy cost is about 11 kilojoules per mole. And then when we're looking at hydrogen and methyl, their energy cost is going to be about 6 kilojoules. All right, so this is how you're going to be finding all these energies, confirmations, and determining which one is going to be more stable. If you have any questions, or if you have any comments, feel free to leave in the section below.